So we've looked at a lot of integration techniques. We've looked at trig functions. We looked at e to the power x and e to the power negative x. We've looked at x to different powers of n. We looked at 1 over x. We looked at additive properties, constants, whole bunch of different things. And like most recently, u substitution and integration by parts. So of all those, we haven't really talked about how the limits, right, the lower and upper limits are affected, right? What properties how they come into play. So we're going to talk about them. It's going to seem very trivial, so that's why this is a short video. But the importance of these properties comes into play when you're looking at a larger problem and you're looking at physical systems. And it's really easy when you're looking at engineering problems, when you're looking at the physical system, to forget the math component of it. And this is where the limits properties do play an important role in thinking about things from a physical, conceptual perspective and connecting it to the mathematical component. So like I said, I'm going to show you the 3 properties of these limits and show you the areas under the curve, and I think it's very intuitive once we show these. 3 interval properties that we're going to look at are, first, the reverse interval. That's saying the integral of a function from a to b versus that of b to a, right, where we swap the upper and lower limits, is just equal to the negative of each other. Okay. The second one is a 0 length interval. This says that if we have the same lower and upper limits, right, they're both the same value, then this will equal 0. And then the third is if you have the integral of the same function, and we take one from a to b and the second one from b to c, then that's the same as taking the integral from a all the way to c. What we're going to look at is graphically what this looks like, and we'll discuss briefly when this can be useful. So first, the reverse interval. So the concept is we're used to taking limits, a lower limit of a smaller value than the upper limit, like from 2 to 5, let's say. We're not used to, we haven't seen, at least in the videos that I've posted so far, the reverse of that. We haven't seen from 5 to 2. So you might ask, when would you actually have that case? Well, the variable x may not have a directional dependence. Now, if it was like a dt, like a time dependence, then most likely your interval will go from a earlier time to a later time. But if it's position focus, then you might be moving like you might be tracking a particle from a point 2 to 5 centimeters. But it can easily be moving from 5 centimeters to 2 centimeters. So the reference and coordinate system may not have as much significance as the process itself would have. And if it's in the reverse order, it might be useful to put the negative sign just to flip it back, so mathematically it's a little bit easier to work with. So let's look at an example of what this actually graphically looks like. So let's say my function is just x, right? The linear 1 times x. And I have the conventional case where I have my small lower limit of 1 and a larger upper limit of 5. And I take the integral, we know how to do this from previous video, and I get a positive area, right? And so in this case, my lower limit, in this blue arrow showing it, starts here and it goes over here. So this is considered a positive area. What if I flip this? What if I take the same integral and then I take a lower limit of 5 and an upper limit of 1? So now I'm going to go in the reverse direction, reverse from convention. In this case, we would look at this as a negative area, right? So I take the same integral. Now my upper limit is 1, so I have 1 squared minus my lower limit of 5 squared. In this case, this will give us negative 12. The case where I have upper limit of 5, I get 12. When 5 is my lower limit instead, I get negative 12. So if instead I take the integral of negative x, like this is showing right here, Then, and I want to match this case right here, then this would match if I have lower limit of 1, upper limit of 5. In this case, convention, this is considered a negative area. So this is also negative 12. So these two, the green equation and the orange equation, are equal to each other. Okay, that's all it is. Simple, straightforward, but it comes most of the time where you would use this is if you have the green function form and you have this integral and you might want to change it and just rewrite it in this form. Sometimes it's a little easier to think about where the lower limit is a smaller value than the upper limit. Okay, zero length interval. This case where you have lower and upper limit the same value, this will give you a area that's equal to 0. I think this one's pretty apparent and it's easy to see visually. But then the question you might ask is, why would you even do this? Well, it might not be an intentional thing, right? You might be solving the work done on a system, force times change in position, or work can be also pressure times change in volume if you're looking at something from a thermodynamics perspective. And you might have some problems where you have a pressure distribution and you do have changes in volume, and then you come to a process where the pressure changes, but the volume doesn't. And that would be represented with the same upper and lower limits. And to recognize that that's a case when this is equal to 0 can be difficult. Now, once I think a lot of you are learning the math component now, but once you learn the engineering or physics piece, sometimes it's difficult to kind of switch gears in your head, right? If you are focused on the math piece and you're not thinking about physically what does this actually represent, that can be a problem. Or if you're only thinking about the physical component, when you have a case that looks like this, it's not always immediately obvious if you haven't done it a few times that that would just equal 0. So let's take a look at why it equals 0. So here I just give you a different example of function x squared, right? So there's my x squared equation, area under the curve. First I say from 2 to 4. So there is a difference between my lower and upper limit. Now let's bring the upper limit closer to my lower limit. Let's look at 2 to 3, right? So obviously a smaller area, right? I back this in here, but it's still non-zero. And then if I back it all the way in, right, what's the idea? If the width, the delta x, right, this interval component goes to 0, then the area would go to 0, right? So this is an example. It's so thin, it's basically a line, and you can see it mathematically, right? So integral of x squared is 1/3 x cubed, upper limit 2, lower limit 2. If I plug in my upper limit 2 cubed, my lower limit 2 cubed, they will always cancel out, right? So whenever you have a case like this, where the upper and lower limits are equal to each other, you don't need to take the integral. Just set it to equal to 0. Okay, the last case here, we have an integral a to b, then the upper limit becomes the lower limit on this case, b to c, then you can just say that it's equal to a all the way to c. And so this one's very nice graphically. So I'll take a new function, x cubed in this case, take the integral. In this case, I go 1 to 2. And then I'll take the same integral, but I'll use the upper limit as my lower limit, and I'll take it one step further. So I go 1 to 2 first. Now I go 2 to 3, right? So that's what's shown here. And so this is my orange first case is right here. This is my second case right here. And then my third case would be combining the two of these. So combining it, I'll take the integral from 1 to 3. So this one's 1 to 2, this one's 2 to 3, and this combine 1 to 3. And it should be the sum of these. So let's take a look. Here, for this first case, I have 3.75 as the area. In this second case, I have 16.25 as my area. This third case, I have 20, which is the sum of these. And so we can see when I plug in my lower and upper limits, 3 to the fourth minus 1 to the fourth, divide by 4, I get 20. And it makes sense that this would happen, right? So if I literally take this equation and add it to this equation, the 2 to the fourth, the middle term, right? That middle, the upper limit here and the lower limit here will cancel, right? This one's it's positive. Here it's negative. It will always come out that way because the signage is literally just applying the lower and upper limits. It has nothing to do with the function itself. So regardless of what the function you're integrating is, this can be applied. So these three integral properties are very useful. They're relatively easy to see. Again, this case is useful if you have something with a generally considered reverse order of limits. Just swap them and put a negative sign in front. This one's useful so you don't even have to take the integral if your lower and upper limits are the same. And this one's useful because if you have these two, just combine it into one integral and apply the limits one time rather than applying it 2 times and then adding them together. So now we have a lot of tools. We have the integral properties, we have u sub, we have integral by parts. Now we have these properties. So we can piece all these together now into real life application engineering and physics properties where we actually do take integrals. And so you'll see how we actually apply these into physical systems.